In this video I'm going to show you how to make an Lpc spectrum of a part of a sound. An Lpc spectrum is a spectrum that does not show you the source part of the signal. It tries and it gives you an estimate of the filter part of the signal. So an Lpc spectrum is a good kind of spectrum to use if you want to make an estimate of the formant peaks without being confused by looking at the harmonics. So we're going to use the Jones CV file again. So we'll open it, and again we'll use cardinal vowel 3. And just to make life a little bit simpler, I'm going to extract that so we've got a little bit less to work from. So I shall extract that and use it. Have the time set at the beginning to be 0. I'll rename that just so I don't get confused. So make sure it's highlighted, click the rename button, and I'm going to rename it CV3 for cardinal vowel 3, and you can see it's changed the name. Now the next step is to go to this button here where it says Formants and Lpc, and what this is going to do is to apply some digital signal processing to the short file that we've got there, and it's going to work out what it thinks the filter for the signal is, extracting or setting aside the source. And the way that it's going to do this is by using a method called LPC, which stands for Linear Predictive Coding. You can read about that in any textbook. Peter Ladefoged describes it in Elements of Acoustic Phonetics, and Katrina Hayward also describes it in her book. We don't need to worry too much about the details. There are various LPC methods, and the one I'm going to use is autocorrelation, which means that it's going to just compare one sample of the waveform with another sample of the waveform a little bit shifted, and it uses that as the basis for the estimation. Now when you click that, it produces you a window, a dialog window with a number of options. And the first of these options is the prediction order, and this number matters for getting a nice accurate spectrum out. In order to get this, you need to know what the sample rate of the recording is, and the sample rate for this recording is about 11,000 Hertz. What we're going to estimate is that there's one formant for every 1,000 Hertz of recording that we've got. So in a sample that's recorded at 11,000 Hertz, we're going to estimate that there are 11 formants potentially. Then we apply a rather simple formula to that. We take the number of estimated formants, which is 11, we double it, which is 22, and then for the sake of safety we add 2, which gives us 24. So the prediction order here is going to be 24. It's probably best to leave the window length, the time step, and the pre-emphasis frequency as they are. So hit OK, and you can see that PRAAT has now made a new file, which it's called LPC of CV3. Now we're going to go back to our original sound file, which is here, and we want to get the spectrum of a particular part of the signal. You can't get a spectrum, well, you can get a spectrum of the whole signal, but it's not a very accurate or worthwhile enterprise doing that. Most of the time you want a spectrum of a very small sample of a signal. So let's choose one from right in the middle. Right in the middle is usually a good place to get a spectrum from because it's where speech signals tend to be most stable. So around the middle is going to give us a time value. You can see up here at the top of the waveform a time value of around 0.664. So just keep that time in mind. And now we're going to go back to the LPC file, and we're going to go extract to spectrum slice. And here it asks us for a time, and what we want is to make sure that this time is the time that we wanted from the waveform. So we wanted 0.664 seconds. So it's going to calculate what the Lpc spectrum is at that point in the file. So we go OK. And now it's made another object for us, which is helpfully called spectrum. So here's spectrum of cardinal val 3. And if we go view and edit, we get, you see, another window up. This window shows the spectrum. A spectrum has got frequency on the horizontal, the x-axis, and amplitude on the vertical axis, the y-axis. And each one of these peaks, so here, and here, and here, corresponds approximately to one of the formant peaks in the signal. And when PRAAT is estimating the formant peaks, what it's doing is calculating the highest point in the spectrum and telling it to you. Now, this is not a very good or accurate method for calculating formant peaks yourself. You can have PRAAT do it more accurately, but this is a nice, useful visual tool for looking at speech. What you're seeing here is F1 there, F2 and F3, but what you're seeing is if you like, a horizontal slice through the spectrogram. If you think of the spectrogram as a more 3D representation of speech, with the peaks of the formants blacker, darker on the spectrogram, and the troughs in the spectrum correspond more approximately to the quieter, whiter parts of the spectrum, of the spectrogram. So here, around 1282 Hz in the spectrogram, you can see it's kind of quiet because it's white. There's not very much energy there, and that's not too far off where the trough in the spectrum is at 1345 Hz. So that's how you can generate spectra in PRAAT.